Hello everybody, this is lecture 4 of measurement and instrument course. Today we will continue on the error. We speak before about two types of error, systematic error and random error. So we will continue on the random error. So the error can be a systematic, which is the sources of the systematic error due to the environment inputs. So the connecting leads, so the reduction of the systematic error using careful instrument design, the calibration, high gain feedback, intelligent instruments. So all of these we speak about before. The other type we call it random error. Random error is caused by unpredictable variation in the measurement system, and maybe they are small perturbation in the measurements either side of the correct value, so maybe positive or negative occur in around the correct value. So the random error can be eliminated by calculating the average of the number by repeating the measurement. So we take a measurement, a number of measurements, and then we may be taking the mean, x mean, to total number of measurements over the number of measurements, or the median, which we will take the right one in the middle of all the values that we take it by order all of the measurement value in ascending order. Okay. Now, for example, for the set A that you see it here, x mean equal to the number, all of them over the total number of them, 11 measurements. X median, we take the value in the middle of all of them. So you see here 5 and here 5, this is the middle one. And again for this example, okay. So, and again for this example, as the number of the values, as the number of the measurements increase, the value of the mean, the value of the median tend toward the value of the mean, so they be close to each other, okay, as the number of the measurements increase. Now we have another thing to measure from the statistical analysis. We have here the deviation error, so how it's deviated from the mean value. So any value or x value, any measurement minus the x mean to see the deviation. If you take the summation over the square of all of the deviation, and you divide it by the number of measurements, then you will have the variance, and the standard deviation, you take the square root of the variance. Okay, this all related to each other, and we may use the sigma, this one. Okay, now, and for the variance we may be sigma square, so square, you remove the square root. So you can calculate all of them. The variance sigma is the standard deviation for each set that we have before. Now you may notice that the smaller the value of v and sigma, then the value it range between maximum and minimum value of the two sets. Okay. So we can specify that as it's, if you draw the value in set C, for example, the measurements, you will see that all of them make this shape. As you, this is, we call it histogram, to see how the distribution of the measurements around the value, the correct value of the value that you take the measurements over. Okay, so if you increase the number of measurements to a very high number, then you will see that this deviation, here this is value is very large, the range that corresponding to each here block. So if you increase the value, the band is very gets smaller, and you see this shape. This shape we call it frequency distribution curve. Here this is the frequency, of each value, how many times it occurs in all the measurements that you take, and the value of it. This is what we call the value of the deviation. Okay, so the value of the deviation here, this is the deviations, and the value of the frequency, how many times it occur in the all the set that we have. Okay, now we want to know the area under the curve. This is from the algebra and probability courses, so you may remember that. So this is, here we have the area under the curve. If you take from minus infinity to infinity, you will have 1, all the area under the curve. So but we are interested in an area from minus infinity to a value, for example, which we call it the cumulative distribution function, CDF. Okay, so this is having a value from 0 to 1 when all of the area under the curve is considered from minus infinity to infinity, less than 1 if you consider from minus infinity to d1, for example, or from d1 to d2. Okay, now let's see, this is this shape or this distribution, we call it a Gaussian distribution, and it have a value, the function, this is have a function as you see here, with a m mean and sigma as a standard deviation, and the error in this value, if you take the d equal x minus m, so the error frequency distribution, you remove x and you put d here, x minus m, and you put d. Okay, so this is the value of the error frequency. Now we will define some equations that maybe you can use it in the mathematical analysis. So z equal d over sigma, d here this is d, x minus m, the mean, and the sigma is the standard deviation. So d over the sigma, it's equal z, which is giving, if we put z in the same equation as the Gaussian distribution, we have now a new Gaussian distribution, but with 0 mean and sigma is 1. This is the standard Gaussian distribution. Okay, we name it standard Gaussian distribution. Okay, this is Gaussian distribution because it's have m which is equal to any number and sigma is not equal to 1. When m equal to 0 and sigma equal to 1, then we have a special case of the Gaussian distribution, we call it standard. Okay, this is the value for the Gaussian standard Gaussian distribution. We have all the values here. Okay, so this is the z and this is the value for f of z. Okay, now let's see how many measurement data, for example, is between or outside the deviation boundary, outside the sigma. If we have here minus sigma and plus sigma, outside the sigma, how many measurements is greater than sigma, greater than the standard deviation. So for example here, b equal to e, the probability of e less than minus sigma, and or e higher than plus sigma. So both of them you take the summation. So e equal to minus sigma, then z equal to minus 1. So you take from z is equal to minus 1, then the probability that it's z is equal to minus 1 is the probability is 1 minus f of 1. Okay, you put the f here, f of z. So f of 1, this meaning that z equal 1, so we will take this value. Okay, so 1 minus 0.413, it's this value. So this is from the Gaussian table. This is an example of the table. There is a large examples of this table to be more accurate. Now let's see here the similarity for the other side, for higher than sigma. So this is the value. So then the probability of the deviation to be less than and higher than sigma is equal to 31.74. This is the measurement outside the boundaries, higher than the boundary, and 68% of the measurements is inside here, inside this place. Okay, now this is calculation again. You can calculate it by your hand. Outside the sigma plus and minus, it's inside 68, outside the 32. If you take 2 sigma instead of 1, you see that's 95.4, it's 4.6 percentage. And here he calculate for different value of sigma. Now we will calculate a standard error of the mean. The mean maybe have some error again, so alpha equal to sigma over the square root of n. N is the number of measurements. Okay, and then you take the value of x as equal to x mean plus or minus alpha. So plus or minus, this is the mean and this is the error in the mean. Okay, this is happening when the finite data set and the true data set is having difference between each other. Now the measurement x mean so the standard error of the mean, we have it here as sigma alpha equal to sigma over the square root of n. So here I have the mean and plus or minus the error in this mean. Okay, now we have the set C. We can calculate the mean as before, the v, the variance, the sigma, the value of the sigma, and we can use this equation to calculate the alpha. So any value, we have it here as the value of the mean plus or minus the value of the alpha. Now maybe you can calculate the alpha as higher or lower for the sigma. So 2 sigma equal to 3.676 on, and the alpha will be different for different value of the calculation of sigma, for example. So you may calculate it as like this for the 95 confidence limit. Okay, this is from this table. Here we have 95 confidence 0.4 or 1.96 for the confidence. Here the confidence that's the value will be for sure will be within this boundary. It's 68%. So we want to make sure that this is the maximum and limits for the error of the measurement. Okay, now the estimation for the this here for the 95% confidence limit, here we have again the 1.64. difference is very low. We will use this equation instead of 2. Here we use 2, but here use this for the error. Okay, so for example, the value here for the sigma and the alpha is these values. He asked you to calculate how should the mass value be expressed under 95 confidence interval. So you will use this equation to calculate. This is a very straight value, and then you will say that the mass value should be therefore be expressed at plus or minus the value that we have here, the error. Okay, now another example. Here the same again, you calculate the value for the probability that's between 0.1 and 0.1. this is from the table. Then you'll have this value 0.0796 multiplied by the all total number of transistor. You get the number of transistor that's having the gain between 19.8 and 20.2. For the greater than 17, this is equal to x higher than 17, which means that the z equal to minus 1.5. This is again from the from the table that we see before, then you will have the value for the table from the table, and you will just multiply it by the number of transistors to get how many number of transistor will have a current gain greater than 17. Okay, that's it for today. Thank you for listening.